I'm Tarun Sebolu, 23BC1016, and I'll be talking about my DA topic, applications of finite automata in search engines. So I'll be talking about the various components of search engines where finite automatas are being used. This is spam filtering, keyword matching, auto-completion, spelling checking and correction, natural language processing. So let's get started. What are search engines, first of all? We know Google, we know Bing, DuckDuckGo, Opera, Firefox, various search engines that help us find information related to our query. So one of the techniques, keyword matching. So when I ask a query, there are a few words that are really important to the query. So if I ask, what is a search engine? The word search engine is a really important keyword for my query. So we use search engines use finite automatas to find these keywords in the query given by the user. I'll give you another example. What is the density of iron? So the keywords would be density and iron because the search engine needs to output density of iron. So it needs to know of what material it should give the density of and what information about a material that it should give. So density and iron both are keywords here. And next would be spam filtering. This is kind of like a broad topic when it comes to search engines. Uh, Spam filtering, uh, it, it's about finding relevant data in huge amounts of websites that search engine can go through. Search engines go through these websites and assign them tags about their data. The keywords that can be found in the data in their website, it assigns them as tags to the websites. And spam filtering is about eliminating websites or information that is not relevant to the query and only giving relevant information about the query. So you use finite automatas as these are really fast when it comes to matching words or finding keywords or finding tags of a website. So finite automatas are used to find information relevant to query and give the website as results. So this is also a reason why you see most relevant websites at the top and least relevant websites at the bottom. So next crucial component of search engines are autocomplete. So autocomplete is really, it's a quality of life. It's a recommendation of completion of the word or the sentence of the query. Suppose I want to input care. That's what I want to input. So I'll get started. So I'll be at Q1. I'll give the input C. So in the search engine, I'll be traversing the automata from Q1 to Q2. So right now there are too many words that start with C. So the search engine wouldn't give any recommendations for auto completion. So next I input A. So I'll be going from Q2 to Q3. So at this point, the search engine would be like Q6 is a final state that is one transition away from Q3, which is pretty close. So it might recommend us the word cat as an auto completion suggestion, or it might even recommend K or cart. So suppose I give the next input, next letter R, it will go from Q3 to Q4. Now the search engine in this scenario has two options, either recommend us K or recommend us cart. Most search engines recommend K or cart based on the use of the word or number of results on the which word would be relevant based on the previous queries of the user or which word is globally used more often. That is how autocomplete works. And if you see this data structure, it looks really close to a prefix tree. It's called trie data structure in data structures, DSA. That is how these automatas are built. These automatas are also pre-computed on the English dictionary. If you're searching in English language, they're pre-computed on English dictionary, and That is why they're really fast when it comes to matching and giving us suggestions for auto completion. So the next topic would be spelling check and correction. This is a really important topic for search engines because we as a human tend to make a lot of mistakes when writing our queries down. In this example, I wrote, what is finite automata? Obviously very wrong. Finite, there's a spelling mistake here. So the Google search engine sees this finite word and it autocorrects it and gives me a result what is finite automata. So it corrected the finite to finite. So this helps search engine understand our query better and helps give relevant information as output. So how is this done? The basic method is lexicon based matching. It is a fast it is really fast because we only ever move forward in the tree or the automata here, and it is also covers in real time, and it is also pre-computed on the English dictionary. So we use lexicon-based matching mainly to find if the given word is in the dictionary or not. That means if the given spelling is correct or not. Suppose I wanted to type out apple. Okay, that's what I wanted to type out, but I made a mistake. So the thing I typed out is APPE. So I'll be starting at Q1. So when I give the first letter A, I'll be going from Q1 to Q2. I give the second letter P, go from Q2 to Q3. And I give the next letter P, go from Q3 to Q6. Okay. So now I give the letter E and I stop. So this is my word. And there is no transition from Q6 to any other state with the letter E. So the search engine sees this. Fine. So there's no transition. Thus, it declares that the given APPE word has a spelling mistake. These are costly to pre-compute, but once pre-computed, they are really fast to traverse through. So that's how it finds errors or spelling mistakes in the given words. So, so a better method, this is for correction also. This is called Levenstein automaton. This is one of the examples of a finite automata designed to also correct itself, correct the word, and how it corrected from finite to finite. It is possible to Levenstein automaton. So, what is the base of Levenstein automaton? It is known as Levenstein distance. So, if I have a word, let's say eat, okay, I can make changes to it. What kind of changes can I make to it? I can either insert a letter, delete a letter, or substitute a letter for another letter. Suppose if I add a letter, if I insert a letter B at the start, it becomes B. Or maybe I delete the letter E, it becomes at. Maybe I substitute E for B, it becomes a bat. So these single character edits like insertion, deletion, substitution are allowed. So the number of these single character changes allowed is known as Levenstein distance. So I gave another example here for class. Insert P in between C and L, delete A, or substitute E for A. All this is for Levenstein distance 1. So going on to the next slide, this is a finite automaton for the word food with max Levenstein distance of 2. So I'll give an example. Hmm, let's say the example is FID. Okay. So if I compare it to the actual word food, my bad. Okay, if I compare it to the actual word food, I can see that F remained how it is. I got substituted in place of the first O, and the second O got deleted, and the D remained as it is. Okay, so it would be FID, FOOD. So we will traverse through this automaton. So first things first, what is this upward transition from 00 to 01 and the star? The star represents any character. So any character transition from 00 to 01. So here this here this upward transition represents insertion. Here it's inserting at the start of the word. So this upward transition is any character insertion at that index. And this diagonal transition with the star represents substitution. Any character substitution instead of F here. Or if it's here, any character substitution instead of O. And this another transition, this null transition, is represents deletion. Uh, so let's traverse to the entire. So let's traverse to the finite automata for the given example FID. So initially I start here. The first letter is F, so I reach 10. Next letter is I, so it's any character substitution in place of O. So from 10, I'll be going to 2, 1 because it's substitution. It's a diagonal transition. Next, next the letter O got deleted. So it would be null transition from 2, 1 to 3, 2. It would be null transition. So the last, right now I'm 3, 2, and the last letter is D. Transition to 4, 2. 4, 0, 4, 1, 4, 2 are final states. So if I reach the final state, the search engine understands that the given word FID is actually wrong and it actually means food. So the search engine understands that in this way. This finite automatas, usually we don't have these null transitions and they're eliminated when they're actually represented in the search engines. We won't be doing that because it's too complex. So next topic, natural language processing. This is a crucial topic. So natural language processing or NLP is a field of artificial intelligence that enables computer to interpret and understand human language. So what it means is we are training the software to enable it to understand the human language, to enable it to understand English, for example. Uh, so this software finds hidden patterns in this language, finds hidden patterns. So we help the search engine understand the natural language, to help it find patterns more efficiently. So methods like tokenization, parts of speech tagging, or named entity recognition. I'll be talking about more. I'll be talking about them more later. So let's get started with tokenization. Suppose I have a sentence. I don't like eating in mess. It's too complex for an AI to understand. So we break it into smaller parts called tokens. So I don't I don't like eating mess would be tokenized in this way. I would be become I would be becoming I. Then the word don't is broken up into do and not. Like eat is broken up into eat and ing, in and mess. All this is made possible through finite automatas to find these patterns to be able to break up the words of the sentences. So moving on to the next one. It's parts of speech tagging, one of the really important topics in natural language processing. So we use FAS here, finite automatas, to assign grammatical categories to the sentences, to the words of the sentences. Suppose the example here, the cat sleeps on the mat. We assign its grammatical category like determiner, noun, verb, preposition, adverb, adjective, and so on. So the simple application isn't scalable because we have to give the dictionary and we have to give what the parts of speech for the each word in the dictionary. and it cannot identify ambiguity. Suppose I have a sentence like, I like to run. Run would be a noun here. In this context, run would be a noun. But if I say, I am running, running would be a verb. So simple application wouldn't be able to distinguish this ambiguity. So that is when hidden Markov model comes in. It is a probabilistic finite state automata. So what this is its transitions are based on a probability. So the search engine is trained. So it's the AI is trained with a large amounts of data set with large amounts of examples. So that when it encounters a sentence like that, it's a great one. It finds that the probability of the word one being a noun is some amount, and the probability of it being verb is some amount, given the context of of the words before it. That is also important. So based on that, it assigns probabilities to each word, mapping it to its parts of speech tags. So the next topic would be named entity recognition. This is also a really important topic for natural language processing, made possible through finite automatas. So it categorizes words in the sentence into categories like person, organization, location, dates, numbers. This goes hand in hand for keyword recognition. So I have an example here. Apple Incorporated was founded by Steve Jobs in California in 1976. The search engine has to go through this, find the keywords, and assign them their named entity recognition. So, what am I talking about? Apple Incorporated, is it a fruit? No, it's an organization. So, it should be able to tell that Apple Inc. is an organization. It should be able to tell that Steve Jobs is a person, and California is the name of a location, and 1976 is a date. All this is made possible by finite automatas, and it helps in natural language processing and helps search engines deliver better results for the queries of the user. That's all. That's all about my topic. Thank you.